For this differential equation, 2y double prime plus y prime equals 0, let's find solution using characteristic equation, and let's also find a power series solution. So let's start by solving this equation using characteristic equation, which will be 2m squared plus m equals 0. Next, I'm going to factor out m, so it's m times 2m plus 1 equals 0, and then m equals 0 and m equals negative 1/2. And now based on this, the general solution to the differential equation is going to be c1 times e to the power 0 times x plus c2 times e to the power negative 1/2 x. And of course, 0 times x is 0, e to the power 0 is 1, so I can rewrite it as y equals c1 plus c2 times e to the power negative 1/2 x. Okay, next let's find a solution to that same equation, but in the form of a power series. For that, we start, in step 1, we start by assuming that the solution to this equation is going to have this form, the series with n that starts at 0 and goes to infinity, c sub n times x to the power n. That's the power series. We'll need to plug this solution into the equation, which means that we need to find the first and the second derivative. So the first derivative is y prime, summation, power n goes in the front, so c sub n times x to the power n minus 1, and we have to start n at 1 so that the starting power of x is 0. And then the second derivative is summation. Now this power goes in the front, so it's going to be c sub n times n minus 1 times x to the power n minus 2. And then this time summation I'll start at 2 once again so that the starting power is 0. Okay, now I'm ready to plug this into the equation. So equation is 2y double prime plus y prime equals 0. So 2 times y double prime, it's going to be 2 summation, and goes from 2 to infinity, c sub n times n minus 1 times x to the power n minus 2, and then plus y prime. So summation n goes from 1 to infinity, c sub n times x to the power n minus 1 equals 0. And the next step is to combine like terms. In other words, we want to add those two series. And to add these two series, we have to do a few things. So first, we're going to put this coefficient inside the summation. And then next, we have to double check that the starting powers are the same. We already did that, but just to double check, right? So n starts at 2, and then the starting power is 0. The starting power of x, right, is 0. N equals 1, so the starting power of x is 0 as well. Okay, so that works fine. And the third thing that we have to check is whether indices start at the same number, and obviously they don't start at the same number. So what we're going to do, we're going to reset both indices. I'm going to use k instead, and I will just set k to start at 0 for both. Okay, so if k starts at 0, and that means that this power has to be k, right? Remember, the starting power is 0, so if k starts at 0, then this has to be k. Well, that tells me the connection between k and n. It means that k is the same as n minus 2. And if k is same as n minus 2, that means that n is, if I add 2 to both sides, I'll see that it's same as k plus 2. That means that everywhere n will be replaced with k plus 2. That's k plus 2. That n is k plus 2, and that is k plus 2. Okay, so I will rewrite it in the next step. And then, similar idea here. Well, if I want to start at k equals 0, the starting power of x is 0, so that means that that has to be k. So then k here is n minus 1, and then n is, I add 1 to each side, k plus 1. Okay, so subscript of c will be k plus 1, and this n becomes k plus 1. So let's write this all down. That's going to be step 2. Reset indices and collect like terms. So summation, k goes from 0 to infinity. Remember 2 we placed inside the summation. So it's 2c sub k plus 2 times k plus 2 times, now here I put k plus 2, but then I subtract 1, so that becomes k plus 1. And then x to the power k, of course. And then the next series is k goes from 0 to infinity, c sub k plus 1 times k plus 1 times x to the power k equals 0. Okay, now I have same indices, I have same starting powers, I don't have any coefficients in front. It means that I'm ready to combine or to add those two series. So here's that summation symbol, k goes from 0 to infinity, and I'm literally combining those two expressions in one. And now, since we already did examples before, you know that the next step would be to factor out x to the power k. See how each general term has x to the power k? So when we add them together, that can be factored out. I'll just do it all in one step. So 2c sub k plus 2 times k plus 2 times k plus 1. Now that will be outside. So I'll continue with plus, and then c sub k plus 1, k plus 1. Now I'm going to close the brackets, and then x to the power k, I factor it out, it's right here, outside, equals 0. Next, to solve this equation means that we either have to set x to the power k equals 0, but we already talked about how this is just a trivial case and we're not going to consider it. But the second case is to set that expression equal to 0. And that's what we do. So 2c sub k plus 2 times k plus 2 times k plus 1 plus c sub k plus 1 times k plus 1 equals 0. Now this equation is the recursion formula, and it relates coefficients of the power series in a certain way. To see that a little bit better, what I'll do, I'm going to isolate c sub k plus 2. So I'm going to leave it on one side and move everything else on the other side, which means that I have to subtract this term, right? So it's going to appear on the right hand side with a negative sign. And then I will divide by everything that stands next to c sub k plus 2. So here it is, c sub k plus 2 equals, okay, that's now on the right hand side with a negative sign, negative c sub k plus 1 times k plus 1. And then I'm going to divide by everything, all the factors that are next to c sub k plus 2. So that's 2 times k plus 2 times k plus 1. K plus 1. Okay, it looks like k plus 1 can be divided out, and that's what we have left. So this recursion formula allows us to find coefficient of the power series based on the previous one. But this is not quite what we need. We want to be able to express coefficients of the power series in terms of just one number or sometimes two numbers, but just in terms of some specific coefficients. And to do that, we're going to perform next steps. And before we move on with step 3, let me just add notes for step 1 and step 2. So step 1 was substitution. That's where we need to plug in y and or its derivatives into the original equation. Now in step 2, we needed to add the series. For that, we first had to reset indices. I'm going to say reset and add series. Right? And now in step 3, I already copied down our recursion formula. Well, we're going to perform iteration, which is taking the first few 4 or 5 values of k, it all depends on how soon you can recognize pattern, and plugging those values into this recursion formula until you, again, can see a pattern. I'm going to rewrite this formula slightly differently. I'm going to put c sub k plus 1 on the side, so it's going to be negative 1 in the numerator, and then 2 times k plus 2 in the denominator, and then c sub k plus 1 right here. So I will be trying values of k 0, 1, 2, 3, and as many as I need. So let's start with the first one. So k equals 0. When k equals 0, I'm going to obtain c sub 2 equals, and I'm looking over here, -1 over 2 times 0 plus 2 c sub 1. Okay, so it's -1 over 2 times 2 c sub 1, right? Okay, when k equals 1, I get 1 plus 2, 3. C sub 3 equals -1 over 2 times 1 plus 2. 1 plus 2 times c sub 1 plus 1, 2. C sub 2. So that's -1 over 2 times 3 c sub 2. And now, since we want everything to be connected to just one constant, what we'll do, we're going to replace c sub 2 with what we found it equals in the previous step. So we found that c sub 2 equals this expression. So we'll substitute it into our result here. So it's -1 over 2 times 3. And remember, it's very important not to simplify anything, not to multiply, not to simplify, otherwise it's going to be hard to see the pattern. Times -1 over 2 times 2 times c1. Okay, so that is c sub 2. Let's keep going. Let's do one more, maybe like 2 more. K equals 2. So it's going to be c sub 4 equals -1 over 2 times. So here I have 2 plus 2 times c sub 3. That's -1 over 2 times 4 times c sub 3. Now, c sub 3 we got in the previous step. Here it is. That's all c sub 3. So I'll have this factor, -1 over 2 times 4. And then I'm bringing down all that. -1 over 2 times 3 times -1 over 2 times 2 times c1. Okay, so I think we're starting to see a pattern. Let's do one more, just to make sure. K equals 3. C sub 5 equals -1 over 2 times 3. 3 plus 2 times C sub 4. That's -1 over 2 times 5. C sub 4, that is, okay, so now C sub 4. That's the one we found here, right? That's all that is C sub 4. Let's plug it in. Okay, so -1 over 2 times 5 times, I'm copying all that, -1 over 2 times 4 times -1 over 2 times 3 times -1 over 2 times 2, and finally times C1. Okay, I think we're ready to start talking about the pattern. The way we want to think about it is to connect the index of C with what we can see on the right-hand side. So, index is 5. What can we see here on the right-hand side? I can see that I have 1, 2, 3, 4. I have 4 -1s. Okay, so I have 1 less -1 than the index. What else? I see 1, 2, 3, 4. I see 4 2s. Again, that's 1 less than the index. And I also have 5 times 4 times 3 times 2. And if I wanted, I could write times 1. It would not change anything. But altogether, that's going to be 5 factorial. So that now matches the index. And then C1. So let's try to write this down if that was n. Okay, so instead of 5, we had n. Then how would we write down the general form of C sub n? Well, then we would have to say it's -1 to the power 1 less than n. So it's -1 to the power n minus 1. Then in the denominator, I'll have 2 to the power that's also 1 less. So it's 2 to the power n minus 1. Then we would have, since we had 5 factorial, which matches the index, it means that we're going to have n factorial here. And then, of course, times C1. So let's call this step 4. So recognizing this pattern is step 4. We're going to come back to that pattern in a little bit. But what we're doing right now in step 5, we gonna take what we found about the coefficients of the power series and substitute it back into the solution. Remember, solution is the power series y equals summation n goes from 0 to infinity, c sub n x to the power n. Okay, so I'm gonna expand it. This means that, well, first it's 0, c sub 0 x to the power 0 plus c sub 1 x to the power 1 plus c sub 2 x to the power 2 plus c sub 3 x to the power 3, and so on and so forth. Of course, x to the power 0 is just 1. So have we found any information about c sub 0? Well, no. Actually, the recursion formula that we had, it only involved everything starting with c1, right? So we know how to express all coefficients in terms of c1. So we did not use c sub 0 anywhere here. So it means that c sub 0 is going to stay as c sub 0. And there is no x next to it since that turned into 1. Plus, now, c sub 1 is c sub 1. Everything is expressed in terms of it. So I keep it as c sub 1, x. Now, c sub 2, well, that I can start rewriting and changing and writing it in terms of c1. I can either use this formula or I can look back right here. It tells me what c sub 2 is, right? Either way. So since I have formula right in front of me here, I'll use it. So it's plus negative 1 to the power 2 minus 1, 1, so like that. Then in the denominator is 2 to the power 2 minus 1, 1, times 2 factorial, times c1, and then times x to the second power. Next, plus, so that's going to be for n equals 3. When n equals 3, I'm going to get negative 1 to the power 2 over 2 to the power 2, and then 3 factorial times c1 times x to the third power. And let's do one more for n equals 4. That is negative 1 to the power 3 over 2 to the third power, 4 factorial, c1, x to the fourth power, right? And then I could continue, but I think it's good enough. So what I can observe here is that coefficient c1 is present in all terms, well, except the first one, and that means it can be factored. So what I'll have is c sub 0 plus, now I'm factoring out c1, and then I'm left with the following summation, x plus negative 1, so it's basically rewriting all that. And as you can see, I'm not simplifying much because I will have to go back to that pattern, so I want to have it in front of me. X to the fourth power, and so on and so forth. Okay, now I want to describe this summation using sigma notation, using short notation. So let's think about it. And of course, it's going to be connected to this, this formula. We just have to verify that we choose the right index. Okay, so I have summation here. And now if I rewrite this formula, let's see what happens. To the power n minus 1, n factorial. Of course, c1 is already factored out. I also have to remember that each term contains x, so of course I'm going to have x to the power n here. And let's now choose the correct index, or I should say the correct value, starting value for the index. So we want to make sure that with the setup we obtain everything from here. So I can see that the first term is x to the power 1. So that means that from what value should I start n? So the first term is x to the power 1. Well, then it has to be 1, right? But now let's verify the rest so that we just get x for the first term. So when n equals 1, power on the top becomes 0, so that turns into 1. Power on the bottom right here becomes 0, so it turns into 1 as well, and then 1 factorial is 1. Yes, so the coefficient becomes 1, and that's the term we obtain. And we can also verify it for the next value. So n equals 2, when n equals 2, we're going to obtain this term. So yeah, that looks good. And technically, we can leave this as our solution. So solution to the given differential equation in the form of a power series can be left like that. But remember how we started this equation? Here it is, that's the beginning, with solving it using characteristic equation, and we obtained this kind of solution. Well, it's the same as solution, but it's written in the form of elementary function. So it would be a good exercise to confirm that this solution is exactly the same as the one we obtained. Well, we know that the exponential function e to the power x is expressed in the term of the Maclaurin series like that. So a series with n starts at 0, goes to infinity. And then here we have x to the power n over n factorial. So we should use that to connect this form of the solution to the one that we found in the terms of power series. So I can observe here that the starting value of n is 0, and that's not what I have in my answer right now. And well, it's not looking too close to what I'm trying to get, but we should be able to perform some algebraic manipulations. And then once again, just a note here that we all, like the remaining steps that I'm going to show, is just to prove that this answer in the form of the power series is exactly the same answer as this one in the form of the elementary function. So I'm going to start by fixing all the powers here. So they're all powers n. It means that I will split up power n minus 1, I will split up power n minus 1, and I will obtain the following. So c sub 0 plus c sub 1, summation, and goes from 1 to infinity. So as I separate power n and negative 1, I'll have negative 1 to the power n, and then I'll have negative 1 to the power negative 1. What does it mean? Negative 1 to the power negative 1. It's same as negative 1 in the denominator, right? And then I'll put x to the power n next to it, right here. Then in the denominator, I'll do the same trick with the power. I will separate power n and power negative 1. So I'll have 2 to the power n, and then 2 to the power negative 1, it's the same as 2 to the power 1 in the numerator. So I'll place it here. And I also have n factorial. And by manipulating powers in this way, what I'll obtain, I just obtain a constant. So I have negative 1 in the denominator, positive 2 in the numerator. Well, it's the same as just constant negative 2, which I can put in the front. So my series will look like this. C sub 0 plus, well, actually, no, it's not going to be plus. Since I'm placing negative 2 in the front, it's going to be negative 2 times C1. That's where it is now. And I have summation, and goes from 1 to infinity. And what I have left is, okay, I'm going to do a few other steps to save space and time. What I'll do next, so I don't have those constants anymore. What I'll do next, I will combine everything that has power n. So I have negative 1 on the top, 2 on the bottom, and x on the top. So it creates fraction negative 1/2 right next to x. And that all can be combined under the same power n. So that is negative 1/2 x to the power n. And then I still have n factorial in the denominator, like that. Well, we're getting there. The only difference we have right now with what we're trying to get, or the way we want to connect it to that other form of the answer, is that series doesn't start at 0, it starts at 1. And this is how we can fix that in this case and, in other cases when it's needed. So I'm going to think this way. I'm going to start rewriting what I have. So it's c sub 0 minus 2 c sub 1. And then I'll start summation at n equals 0. What does it mean that I switched from 1 to 0? Well, it means that I created one additional term, right? So here everything started at n equals 1. And then here I have one additional term that I didn't have before. But I cannot just create one additional term. Well, if I create it, I have to cancel it as well, so that overall the sum does not really change. Let's think what kind of extra term we created. What happens when n equals 0? And by the way, I can still write down everything else I have. So what happens when n equals 0? What is the extra term I just added by changing the index? Well, when n equals 0, everything in the numerator is being raised to that power. Power is 0, so it means that the numerator is 1. And then in the denominator, we have 0 factorial. Well, 0 factorial is actually equals 1. It's a little bit interesting the way it works, but yeah, 0 factorial is 1. So it means that I have 1 in the numerator, 1 in the denominator, and overall it's just number 1. So at n equals 0, we get extra term 1. Well, it means that I just added extra 1, and I need to subtract it so that overall quantity doesn't change. But that all happens, since I'm only playing with summation, it happens all in here, so kind of like inside the parentheses. So that negative 2c is still outside. So we're almost there, just literally a few more steps. What I'll do next to clean this up, now I will distribute negative 2c1. So as I distribute it, it's going to be still in front of the summation symbol. And then as I multiply negative 2c1 by that 1 that I'm subtracting, it's going to create one extra term, which I'm going to put in the front. So this is what I'll have. Equals c sub 0, that's this one, and then negative 2c1 times negative 1, it's positive 2c1, so it's plus 2c1. And then minus, well, and the rest, minus 2c1 times that summation, but I don't need brackets anymore. Negative 1/2 x to the power n over n factorial. Okay, and that's what we got. Now, is that what we needed? Compared to y equals c1 plus c2 e to the power negative 1/2 x. That's the answer we're trying to obtain. Keep in mind that c1 and c2 here, they have nothing to do with the coefficients of the power series. These are c1 and c2, the arbitrary constants we picked when we solved that equation using characteristic equation, right? But if I want to match what I have to what I got in the first place using the first method, then this is what I'll do. I can just rename the constants right here. So c sub 0 plus 2c sub 1, I can rename and let's call it c sub 1 star, or we can use capital C1. So I'll keep the star, c sub 1 star, and then that I can rename as positive c2 star plus c2 star. And that is actually now a form of the Maclaurin series for e to the power. And the power of e is whatever we have here inside the parentheses that's being raised to the power n. So it's e to the power negative 1/2 x. And now we can see how those two look identical, right? Once again, all those steps were just to show how those two answers are the same, but it would be completely fine to leave your answer, in one of the previous versions, one of the previous forms, if you don't have to prove answers to be the same, like we did here. So these are the steps for solving that differential equation and obtaining the power series solutions.